Okay, so part two. So I'm going to do the sections 5, 6, and 7 of this talk. So this morning it was about how scenario sets can be linked to risk measures, and then I talked quite a lot about superadditivity and a geometrical understanding of when it occurs for the value at risk measure. So now I'm going to go to section 5 and talk about the relationship to capital allocation or capital attribution, because this is also connected to these sets in rather a simple way. But before I get into this slide, maybe I will just go back to one. I have to go back a little bit. Go back to Formula 3. So what we saw was, in general, this quantile function is bigger than the support function of the convex set. It's bigger than the worst case in the convex set. And you only have equality if you have a subadditive risk measure. So unfortunately, the set Q alpha doesn't give you an upper bound for value at risk. So this inequality is no use for bounding value at risk above. So one of the motivations for the fifth section is actually to get an upper bound for value at risk in the situations where subadditivity breaks down. Okay, so, and that is obtained through an outer scenario set. So here's another way of creating a set of scenarios. For this, I'll assume that we're dealing with a continuous distribution with a density. In fact, that condition is sufficient for the differentiability of the risk measure function. It's not necessary. There are papers by Dirk Tascher where he derives weaker conditions. But let's just assume that X has a density in Rd. It means we can compute the gradient vector of the risk measure function. So the gradient vector is written here with this nabla sign here. And for any risk measure, I define a set O. You can think of O for outer. And the set O is basically the points which are all given as gradients of the risk measure function for different directions, as it says underneath here. Now, what you can show is that for any positive homogeneous risk measure rho, in fact, the risk measure is bounded above. So here you do get the upper bound. It's bounded above by the worst case of lambda transpose X for scenarios X in this set O, which are the gradients. And once again, you have equality for all possible lambda if and only if this risk measure function is a subadditive function on Rd. Okay, so I'm doing this for two reasons. One, because it will allow us to connect these sets with the capital allocation, and secondly, because this will give an upper bound. So maybe just to give a hint why this is true. Well, firstly, this inequality is very simple, and it comes from the Euler rule, or the Euler representation for positive homogeneous functions. It's well known that because of the positive homogeneity of this function, you can write it in this form, lambda transpose times the gradient vector. And then by definition, and then this is obviously smaller than lambda transpose the gradient at points at the supremum of the lambda times the gradients at points u, excluding the zero vector. And this is precisely how I define the set O. So that's how we get the inequality. And then the fact that you have equality throughout for all lambda, or you have equality for all lambda if and only if R is subadditive. Well, one direction is simple. If you have a risk measure which is of this form, subadditivity is obvious. So the more difficult direction is just checking that if this function is a subadditive function, then the O set is contained within the S set. That's what you have to check. I've written down why it's true here, but it's pretty simple to see that a point in the O set is also in the S set. You use, in fact, the convexity of this R function. And from that point of view, R is less than the supremum in the O set, which must be less than the supremum in the S set. and this is exactly equal to R, so you get the equality. But okay, I'm more concerned here with what this actually means. So for a coherent risk measure rho, you can write the risk measure function as the worst case for scenarios X in this O set. And what we've actually found, O is just another description for the boundary of S. It's a way of describing the boundary of S. And so points on the boundary have an interpretation in terms of attributing the risk of the portfolio to the risk factors, to the components of X. So points on this boundary have interpretation in terms of allocation of risk of a portfolio to the components of X, because the risk of a portfolio, as measured by the risk measure, is given by this risk measure function. This equality comes from the Euler representation of the positive homogeneous function. And then we've just seen that this must be equal to the worst case. And let's say that the argument that actually gives us the supremum is X star lambda. And so what we find is this worst case scenario is the per unit of allocation of risk to each component. So that gives another interpretation for the boundary points in this case. So that is true if the risk measure is coherent. For a risk measure that's not coherent, what we do is we get an upper bound for the risk measure. So let us take value at risk, which is not a coherent risk measure. And in this case, I've written this outer set O, I've called it O alpha. Then we know that the value at risk of a portfolio L lambda is going to always be bounded above by the supremum lambda transpose X for scenarios X and O alpha. I think this is largely of academic interest, but it does give me an excuse to create one more picture, which is this one. If you're wondering what O alpha looks like, let's go back to one of those cases where subadditivity breaks down. So it was independent exponentials. The quantile level is 0.72. So we get this phenomenon that there are non-supporting hyperplanes. Well, I've traced in black, I've traced this outer set, O 0.72. And it is true that for any particular direction, if you take the supremum on this black set, you get something that bounds the value at risk above. But this part of the talk is, I think, largely of academic interest. It's a kind of natural question. You know, how much can the discrepancy be between the value at risk and the worst case in this set? But what I really want to do this afternoon in this second part is talk about computation of these sets in practice and what that has to do with stress testing. So here are my general reflections on the problem. So up to now, I've shown the construction of these sets by looking at intersections of half spaces. And I think that's quite educational. You understand how these sets are created, but it's not really practical, especially for dimensions higher than 2. If you imagine trying to create the set by looking at every possible hyperplane, and of course, you can barely draw a picture of it for d equals 3, and you can no longer visualize it adequately for d bigger than 3. So it would be most convenient if we obtained sets which had a simple parametric form, something that we could describe succinctly. And that was obviously the case for elliptical distributions. So the set S rho for any elliptical distribution, you can show that it is an ellipse or an ellipsoid in higher dimensions. So that's easily parameterized, and it's very easy then to check if an arbitrary point in d-dimensional space is in the interior of that set or is outside that set. But I will concede at this point that for a general distribution, it is quite difficult to parameterize these objects and to describe them in a simple form. I'm going to show a class of distributions where you do get quite nice results in a second. If it's not possible to describe the set in a simple way, I mean, what we really need to be able to do is to decide whether any arbitrary point is in the set or outside the set. We need to know, is it a scenario in the set of scenarios that we will consider, defined by the risk measure, or is it outside the set and not to be considered? And so to work out if a point is in the set, we have to be able to compute its depth, because we have this representation that these sets contain points that have a certain minimum depth. And so computing half-space depth is a key consideration. In lower dimensional applications, by which I mean d equals 2 or d equals 3, another way you can compute these sets is if you can compute the depth function, you can just compute depth on a grid, and then you can form the contours of equal depth. And some of the pictures I show will be formed in that way. So I'll restrict attention to value at risk. So obviously I've shown that for expected shortfall and for the expectile, we can construct these sets as well. But for the purposes of the remainder of the talk, the examples will be done with value at risk. And so the set will be the set I've called Q alpha, which is like this multivariate extension of the quantile. So in this part of the talk, I'll do two things. First, I'll consider a class of models for financial risk factors that allow for heavy tails, but also allow for skewness, where it is possible to calculate these sets. It's possible to calculate depth. For this class of distributions, it's possible to calculate depth, half-space depth, and it's possible to approximate the form of these sets in quite a nice way, as you will see. I'll also consider non-parametric estimation, because that exists as well. And in fact, there's an R library which does it. And so I'll mention that as well. Okay, so the class of distribution that I've picked is the class of generalized hyperbolic distributions, although there are some other related classes for which this construction also works. So if you don't know about the generalized hyperbolic distributions, there are a number of reasons why these are quite nice and why they're quite popular for modeling financial returns. For a start, you can connect them to continuous time theory of processes. They are infinitely divisible, or distributions are infinitely divisible random vectors, so they can form the increments of certain Lévy processes. They can have skewness and heavy tails. There are some particularly popular special cases. You may have seen papers that use the normal inverse Gaussian model or the variance gamma model or skew T distributions for modeling returns or changes in financial risk factors. The stochastic structure is that they can be represented as mixtures of normals when you randomize over the mean vector and the covariance matrix. And for that reason, they're actually very easy to estimate from data, regardless of dimension. So whether the data is 2, 3, or 20, or 30, in fact, there's an EM algorithm that will estimate them by maximum likelihood, and it's implemented in an R library, ghype, which works pretty well. So these distributions, they are d-dimensional, and they're basically described by 6 things. There is a location, there is a mu, there is a matrix sigma, which tells you about spread and aspects of correlation, for want of a better word. There is a vector kappa, which is a skewness vector, and then there's 3 other parameters that specify the type and basically the heaviness of the tails. So are the tails of student type, with power law type, are the tails of more gamma type, etc. These are specified by these shape parameters. Now, the interesting thing about these distributions is that the depth, these distributions aren't generally elliptical, unless you set the skewness vector to be 0. But even for quite skewed examples, it turns out that the depth contours are near elliptical. And just to give you an example, so these are real data points, these points here, They happen to be related to yields of government bonds in the UK, so that it's changes in yields, data on changes in yields. It's the 3-year government bond and the 10-year government bond, so a time series of values for yields for these maturities is then difference to get changes in yields, and you get this point cloud here. So there are some positive and negative changes, but it's very skewed. Obviously, this distribution is clearly very skewed. And what I've done is I've fitted one of these generalized hyperbolic distributions. I fitted the normal inverse Gaussian using this G-hype package, and then I'm showing various things for the fitted distribution. The first thing to talk about, these contours here are actually contours of density. So I've superimposed the contours of density. And what happens with the contours of density is they're pulled down to this corner. You can see that they're pulled down here where most of the data are. And so if you pick any of these curves, and we could draw bigger contours, then they don't do a particularly good job of describing the shape of the distribution. If you take this one here, although there are very few points outside down here, there are lots of points around here. So the contours of density for a very skewed, heavy-tailed distribution, they don't do a very good job of describing the shape of the area in which the points lie. So the next thing I do is I'm actually doing two constructions of the depth set. So the first construction is I use this half space construction, and the white area here becomes the intersection of the half spaces. The second thing I've done with a dashed line, I have computed depth, half space depth on this grid, on a fine grid, and then I've connected the points of equal depth. Either construction gives the same thing. It gives a set, it gives a set here. And the first time I did this, I was actually rather amazed, because to the naked eye, this looks like a perfect ellipse. And we're not dealing with an elliptically symmetric distribution. We're dealing with a very skewed distribution. So this looks like a perfect ellipse. It's not actually a perfect ellipse, but it's extremely close to a perfect ellipse. And so analyzing this class of distribution, and also a couple of other multivariate families that have similar constructions, in fact, you find that they have the property that their contours of density are near elliptical. And even if you take very skewed ones and ones with very heavy tails, the elliptical approximation is very good, as I'll show you.
Is there an intuitive explanation why?
This is the intuitive explanation. This is the intuitive explanation coming up. Basically, what this distribution has is there is an affine transformation that we've called here a canonical affine transformation that allows you to concentrate all the skewness on a single component. So it's a linear transformation that takes one of these distributions and concentrates all the skewness on a single component. So this is what's written here. This is a general distribution, and then what is specified in this operation here is a linear transformation or an affine transformation. And you see that what it does is obviously it doesn't change the dimension. This is a transformation that preserves the dimension. It sets the location to 0. It sets the sigma matrix to the identity. It concentrates all of the skewness in the first component of the unit vector, and it doesn't do anything to the 3 parameters that describe the shape of the distribution. So the intuition is here that you can find a transformation that concentrates, if you like, all the skewness in one component, and then the other components are symmetrical. And so that seems to be why it works. There are other classes of model that people quite like for modeling skewed multivariate phenomena. There are the so-called skew elliptical models of Azzolini, It's a different class of distribution. The same thing works for them, even though the construction is different. They still allow the skewness to be absorbed by a single component. Anyway, because of this, it turns out that, okay, so we concentrate on the canonical form because, in fact, half-space depth, or the analog that you get when you look at expectile depth, for example, they are affine invariant. So if you compute the half-space depth at this point here, ax plus b, relative to the distribution of ax plus b, it's exactly the same as the half-space depth at the point x relative to the distribution x. So because of the affine invariance, we can actually concentrate on the canonical form. It's not too difficult to compute the depth numerically. The dimension is not important, whether it's 2, 3, 4, 5, 6, etc. And then if you do that, you see that these models are very close to ellipsoids. So this is a bivariate example. This is the canonical form. And basically, all of the skewness is now expressed in the x direction, and we have symmetry in the y direction. And I've taken actually very quite extreme examples, skew t distributions, skew normal inverse Gaussian distributions, and which is which? I think either the dotted line is the true depth contour and the dashed line is an elliptical approximation, or vice versa. Which one looks more elliptical? I think the dotted one is the true one and the dashed one is the elliptical approximation. These are pretty skewed distributions. This one, the approximation is very good indeed, and this one here, this one perhaps less so, but the contours are near elliptical in this family. And actually, you take the skew, in this class here we have a distribution called a skew Cauchy, which is a pretty extreme distribution, a skew Cauchy. And for the skew Cauchy, rather miraculously, the contours are exactly elliptical for the skew Cauchy. That's rather surprising. So I wrote a paper with a PhD student in Lancaster, Emanuele Giorgi, and we looked into these things. So this is a class of distributions where you can compute these things. And for price change data, it's not a bad family of distributions to consider, because at least you can model heavy tails, you can model correlation, you can model skewness. It's not reality, obviously, but it's a family of parametric models. At the opposite extreme to parametric estimation is the idea of non-parametric estimation. And there is in fact, the ideas of depth, they were invented in the 1950s for non-parametric data descriptive purposes, and the exploring depth in parametric models came later. So to say a little bit more about that, Tukey is quite a well-known name in applied statistics, particularly for all kinds of ways of visualizing data and understanding data. And he proposed the idea of data depth. And that's basically this formula here is the idea of data depth. What I have defined so far, I've defined half-space depth at a point x with respect to the distribution of a random vector x. And I've said that what it is the smallest probability of a half-space that goes through that point. Well, the empirical analog is that you have data vectors. Let's say you have n d-dimensional data vectors, and you compute this quantity for the empirical measure of the data. And so computing this for the empirical measure of the data means basically computing this. You've got a sum, a 1 over n, and then this is the indicator that u transpose xi is less than u transpose x. And that's how you compute empirical depth at a point x. And the intuition is pretty obvious that if you have some kind of you have some kind of point cloud. You have some kind of point cloud, and for every point, you look at the smallest empirical probability of a half space through a point. So you know, at a point here, you would probably put the half space. Sorry, you'd probably put the half space like that. So you had 2 on one side and 4 on the other.
So we can simply say it's the depth of the empirical distribution.
Yeah, it's the depth of the empirical distribution. This is the depth of the empirical distribution. Now, so Rousseau, who's well known for many things in statistics, has worked for a long time, actually since the 90s, on algorithms for computing this. And he has algorithms for computing it for d equals 2 and d equals 3 exactly. And then he has approximate algorithms that work in higher dimensions. And they also give good results for n large also in lower dimensions. And these things, there's an R library that contains them. There's another name for the contours. So when you plot the contours of equal empirical depth, you get a picture which has been called a bag plot. The bag plot, I don't know if it's a great name, but that's what some people call it. A bag plot is basically an iso-depth contour for the empirical measure. And so there's an R package depth. But just to give you a sense of how that works, let me draw a picture, which again is a bit of an excuse to put all kinds of things on the same graphic. But this time I have generated data from a model. All I want to do is understand whether these empirical tools actually work. So I've generated data from a model, and I've generated it from a bivariate normal inverse Gaussian. So these points are just simulated from a bivariate normal inverse Gaussian. So there's a few things going on. The green lines here are the contours of the density, of the true underlying density, and the blue lines here, these are the marginal densities. So these are basically just the marginal densities superimposed. You can obviously see the skewness. The gray lines, that is the half-space construction. So the white set is the true 95% depth set. And then finally, this red line here is constructed using the R depth package. So that's constructed from the empirical measure. So all this is supposed to show is that, at least for this example, the depth estimate is the non-parametric or empirical estimate is close to the true shape for the underlying distribution. However, there are lots of data here, obviously, so that's a good example. So, I merely mentioned that non-parametric estimation is possible in addition to parametric estimation. And there is quite a long literature of looking at this question. I haven't seen anyone really look at, well, the expectile depth and the shortfall depth measures. Basically, we've defined those as new measures of depth, and I haven't really seen any work on computing those empirically. But you could I think, compute expectile depth using basically the same ideas that are used in expectile regression. That's something I didn't mention at the time, but in fact, the quantiles, there is this thing in econometrics called quantile regression, and people got interested in expectile regression before they got interested in expectiles. They basically changed the form of the function that had to be minimized in a regression model. They changed the form of the error function, and they got what was called expectile regression. And that, I think, came before people even got interested in the expectile as a risk measure. So using those techniques, one could compute empirical expectile depth sets. Okay, stress testing. let me finish with a kind of stylized example of how stress testing might work with these sets. So here's the situation. I will go back to the idea that we have a parametric model rather than that we work with a non-parametric model. So I'll go back to the idea that we have a parametric model, and this parametric model describes changes in financial risk factors. And we also have the idea of a function, which I've called an impact function, which says what these will do to a particular portfolio. It could be the trading book of a bank. It could be the balance sheet of an insurance company. And so this is a known function. If I were to give you a set of values for X, you could then revalue the portfolio under these changes and work out what the loss would be. And the revaluation of the portfolio depends on the instruments in the portfolio. For some, it might be what they call mark to market. You just look at the new price under the risk factor change X. For some, it might be mark to model. You might use a Black-Scholes valuation of something, and so you have to then revalue the instrument in the Black-Scholes model under the new values for the inputs to the formula, such as the price, the volatility, or the interest rate. But we'll assume that it is essentially known. So L is a known function. In insurance, for solvency purposes, most companies will tell you that they have model office software. And model office software is basically programming the L function, because if you feed it with changes in things like the term structure of interest rates and market prices, and it tells you what happens to the value of your liabilities in particular, and also your assets, so you can work out if you would still be solvent under that particular scenario. So L is known. And as I've said at the beginning, we could think of forward stress testing or reverse stress testing. So an interpretation of forward stress testing is determine the scenario set. And if we work with value at risk, then the scenario set is Q alpha. If we work with expected shortfall, then the scenario set could be what I called S alpha. Determine the set and attempt to maximize the impact for scenarios in that set. And then when you found the maximizing scenario, you can have a look at it and attempt to understand exactly what is it about this scenario that makes it particularly impactful and worrying for your company. The reverse stress testing could be formulated in this way. That is the idea that you think of all scenarios that would ruin you. So for your particular portfolio, there are scenarios that will lead to an unacceptably severe loss. They will lead to a value that makes you insolvent, literally perhaps, or at least makes investors in your company worry about continuing to invest in your company. So there's some idea of a threshold here that is a severe loss and a failure region. And what we want to do is find the scenario that is most plausible in this failure region. So in the failure region, we want to maximize plausibility. And in this world in this world that I'm describing, the measure of plausibility is the half-space depth. If the risk measure is the quantile, the measure of plausibility is ordinary half-space depth. If the risk measure is the expected shortfall, the measure of plausibility is shortfall depth. And then again, you can examine the maximizing scenario. But for all of these tasks, it will be essential, the essential thing that you always need to be able to calculate is half-space depth at a point X with respect to your model. All of these things rely on being able to calculate depth. And so I'll give a simple example. I would call it stylized because it's really just to understand the thought procedure that I'm proposing here. So it's simple. There are two risk factors, but the impact is non-linear. It's important here that we introduce non-linearity. At the very beginning, I introduced a linear portfolio set simply to get a nice form for the scenario sets. But now in practice, and this is a slight disconnect, you could say, when I use these scenarios, I want to use them in situations where I don't have linearity of losses in the risk factors. So here's an example of that, a stylized example. So it's slightly insurance flavored, or it's something that I created after I had a discussion with a company in Edinburgh, actually, that builds economic scenario generators. So suppose that your company has a liability in the form of a put option on a stock index. This is quite common in insurance when they sell a guarantee. If they sell some product that promises a guarantee, let's say some stock market-based product that guarantees a certain level of return, then effectively they end up being short a put option for those kinds of guarantees. So if you've sold a guarantee based on the value of a stock index fund at a future time point, you end up being short a put option. So we will take that as an example. And in order that you can see these things, we'll eliminate interest rates as a risk factor and concentrate on prices, the index prices, and index volatility as the two risk factors. So we have sold one of these things. We're effectively short a put option because we've sold a guarantee to some policyholders. So we are concerned about mark-to-market losses over a particular time horizon. In insurance, this would actually be 1 year because the solvency calculation is on a 1-year basis. But I'm not stipulating here to begin with what the time horizon should be, although I'm actually going to take 2 weeks. But our concern is for mark-to-market losses over a particular time horizon. So now is t, the future is t plus delta t. And my losses can be expressed as a nonlinear function of the log return of the index, and I'll take the log return of the implied volatility just so that both prices and volatilities don't become negative. I'll work with the log returns. And so the log return of the index and the log return of the implied volatility, basically these are x. These will be x. And there is a nonlinear function relating those two to the actual losses for this time horizon delta t. And I'll suppose that we have a small amount of historical data, and in the example I take about 100, a small amount of historical data to calibrate a model for changes in the index or the log index and changes in the log implied volatility. So the numbers that follow, or the pictures that follow, are based on data which are downloaded from the internet. So the underlying index in this case is the S&P 500, and the underlying index of implied volatility is the VIX index. So for a 2-year period, 2011 to 12, and I've taken a time horizon of 1 week. It's purely illustrative. But I've taken a time horizon of 1 week, and then 2 years gives you around about 100 data. 2 times 52, or thereabouts. And at time t, let's just say that this option is slightly out of the money. It doesn't really matter. You can specify an option which has some particular form. So at time t, it's slightly out of the money. And so this... Oh, these colors are not good colors to project. Yeah, they're a bit washed out in this screen here. These are the default colors of the colored contour plot in R. But this is the way it works. This, if you like, is x1, and this is x2. These are changes in the log price or the log index value, and these are changes in the log VIX value. And these are 100 points here. But what is going on in the background, this basically is giving you information about the losses that you would incur, the mark-to-market losses you would incur over 2 weeks. So you would incur high losses here. So if you're short a put option, so the stock price falls, volatility goes up, high losses here. On the other hand, stock price rises, volatility goes down, you actually make mark-to-market gains down. So these are mark-to-market gains. And if you look at it on the computer, yeah, the coloring is a bit better on the computer. It starts to wash out around 0, and then it becomes purple over 50. So you can see a kind of ribbed effect. And these are contours on which the impact is equal. So contours of equal impact. So scenarios on these lines would lead to the same impact, the same mark-to-market losses. So this picture conveys the information. There's a third dimension here, which is the actual impact on this grid. And let us suppose that we, so the first set I've drawn is Q 0.995. This is based on actually taking one of these normal inverse Gaussian models and constructing Q 0.995. And then I've constructed Q 0.999. And these are the scenario sets. So the idea is that one should maximize the nonlinear function over the scenario set. So one has to decide how big should it be. Should it be the smaller one? Should it be the larger one? Should it be neither of those and a one of different size? But you can see that, if we were to take the bigger one, the loss maximizing scenario is up here. There's a scenario up here, which is the worst one, which leads to the worst loss. But anything up in this corner here is leading to quite severe losses. So maybe everything over 100 is up here in this corner, excuse me. Come back to that. And so the forward stress testing problem is create the scenario set and then look for the worst impact for your particular balance sheet or portfolio. The reverse stress testing problem is like this. Let us assume that we would be ruined. Of course, we wouldn't be. It's unrealistic. But let's suppose we would be ruined if there was a mark-to-market loss over 2 weeks of 100. There would be such a crisis of confidence in our firm that all our investors would withdraw their investments. So this is the ruin region. I've drawn a red line on this contour, and this is the ruin region up here. And reverse stress testing, the idea is that you look at the most plausible way of being ruined. And in this case, the most plausible way of being ruined, well, it's basically the point where the depth set first touches the ruin region. This point up here where the depth set first touches the ruin region, for this particular situation, this is the most plausible way of being ruined in this case. So that's the other way of looking at it. So these are stylized, but let me just give you some conclusions, and maybe these are discussion points. My conclusions are, I think this approach could be actually potentially more useful in higher dimensions, because that's when you lose clear intuition about what affects the loss impact function. If you know about options, then you know how they react to volatility and stock price and interest rates. But if you're thinking of a more complicated portfolio with many risk factors, you're going to lose your oversight of what leads to losses. And so that's where I think it could be useful. Higher dimensions, not very high dimensions, but when you start to look at 6, 7, 10, 11 risk factors. However, I will have to concede that in order to implement this framework, you need to work with classes of distribution where you can either calculate or at least approximate depth. And the reason I included the part about generalized hyperbolic distributions is they are quite a popular family for modeling price changes, which show heavy tails or show skewness. And the nice thing about those is you get very close to ellipsoidal sets. And ellipsoids are very easy sets to work with because you can describe them with 3 things: a location, a matrix, and a size. I will note here that measuring what I've called centrality of points based on ellipsoids, this has a long history in statistics, named after the Indian statistician Mahalanobis. There's the idea of the Mahalanobis distance. And if you use ellipsoids, you're using a Mahalanobis distance. So this provides some justification, or these skewed distributions provide some justification for doing that. One clear use for the technology, if you're told by a regulator or some other knowledgeable person that you should consider such and such a scenario, perhaps stock market falls 30%, 2% parallel shift in the yield curve, and GDP falls by this amount. If you're told you should consider that, then this is one way of trying to put a measure of plausibility on a hypothetical scenario on the basis of historical data. You can say to the regulator, well, the plausibility of this scenario is 0 based on 2 centuries of historical data or something, or probably not that much. Or you can acknowledge that this is not an implausible scenario based on the distribution. And in an economic scenario generation context, that's these companies that build Monte Carlo models, there's some interest in at least being able to rank scenarios by plausibility or centrality in these models. So those are all about possible uses in stress testing. I think also I quite like the fact that when you're doing risk measurement based on VAR, this approach gives very useful insights into when superadditivity can be useful. When superadditivity can arise. And for example, in studying portfolios of defaultable bonds, you get quite nice intuition about when superadditivity will arise and when it won't arise by taking this approach. So it's still work in progress. I hope it is at least interesting, a little bit different to other things you might have heard. And this is an incomplete list of literature. As I've said, the concept of data depth, I'm sure Chuki thought about it earlier than 1975. I think I said 1950 before, but okay, 1970s. These ideas, they crop up in different forms. Multivariate quantiles, studied by Eddy in the 1980s. The construction with half spaces, some people call this trimming, a half space trimming or multivariate trimming. There's literature on that, 1990s. There's some very nice papers involving Rousseau, computing depth functions for distributions, but particularly they're interested in non-parametric estimation. There are other ways of, so I use half spaces. So all my depth measures are based on half spaces, although they change a little bit with the choice of risk measure. But there is a large literature on other concepts of depth which use other objects than lines or planes. There's a notion of simplex depth, for example. So there's some literature on that. And I have talked about ideas that may be found in 3 papers. The original paper I wrote with Andrew Smith. This is in Insurance Mathematics and Economics. This paper about the calculation for generalized hyperbolic distributions is in a Computational Statistics and Data Analysis journal. And then if anyone's interested in this, I can send a draft copy of a forthcoming second edition, which perhaps is the best connection between the scenario sets and the risk measures. Okay, so it's probably time for a few questions, or not, as the case may be, but that's what I plan to say. Gregorios.
You mentioned at some point the allocation based on the Euler approach.
Yeah.
What do you think about the fact that some people are doing the initial VAR calculations and then they allocate based on expected shortfall, so you can somehow mix the measures in terms of allocation. So you can have the VAR calculation for the total portfolio exposure, but then you will allocate back to the.
I know what you mean. So some people who measure risk with value at risk allocate using expected shortfall. They do it because generally they are estimating these things empirically, and it's easier to estimate shortfall contributions because you average over all the scenarios in which VAR is exceeded, whereas to compute VAR contributions, you have to average over scenarios which are at the VAR or very close to it, and there are very few of them. So they do that for entirely practical reasons. Though it makes everything inconsistent because you're measuring risk with one measure and then you're allocating with another. The two things become aligned and consistent in an elliptical distribution, actually, because it doesn't matter which risk measure you choose, you get the same allocation, whether it's expected shortfall or VAR or indeed the expectile. You would get the same allocation in terms of proportions. But if you're not in an elliptical distribution, then it's theoretically inconsistent to do that, but it's done, I think, for purely practical reasons.
I think that some people try to do that in order to eliminate the problem with the subadditivity in VAR. That you could have a huge exposure somewhere, and the allocated capital was negative. So you maybe had like 80% of your exposure within one actual.
Yeah, you can get a negative with VAR. You can get a negative.
But if you expect a shortfall, you see that 98% of the actual capital will be allocated there. So it's like completely.
Yeah, that's true. That's another reason why people do it, to avoid negative allocations. But also, I think
not only the negative, but also the non thing that you could not explain why a huge exposure doesn't allocate capital there through VAR.
But as far as I understood, the main reason was it's just very difficult to compute these things based on VAR. Because what they do is they generally do it by Monte Carlo, and then they average over all scenarios which exceed the VAR.
Yeah.
Another question.
Just one question about the scenario set. Do you assume that you know all the joint distribution of the scenario set? Or just
Yeah. So I'm assuming here that I know the distribution of X fully. So, I mean, I gave this talk without, for example, mentioning the word coppola. And sometimes I'm asked when I give this talk, well, how does this relate to coppolas? You know, if you've got marginal distributions for these risks and then you want a coppola. Well, I mean, you could apply this concept as well. The thing is, it might be almost impossible to calculate these sets. In some strange model that had different marginal distributions in a coppola, I think it would be almost impossible to compute these sets.
If we're doing
that may be so, but conceptually,
Conceptually.
one can extend it to a setting where you have some kind of model ambiguity,
Yes.
like in risk measures. Beyond the law invariant case, you can also consider.
Yes, so that is an obvious way to extend it. Ambiguity, model uncertainty is an obvious way to extend this, because in reality, these things move around. There's a lot of uncertainty about whether that's the right one or whether, you know, what angle it should be. So it's a sort of first attempt to lay out a pathway, but there's other issues such as estimation error and uncertainty about the model itself, which aren't considered at this point. Okay, I probably better stop it there. Thank you very much.